let's say that you have numbers. What were the numbers that you guys were looking at?
5, 4, 1,
5,
3.
4. 5,
4,
4.
You had some complicated numbers also, right?
1, 3,
1, 3,
2.
2. And let's add some more if you wish.
Yeah.
Give me some more. Maybe 7, 8,
0.
0, and I don't know, 4, let's say.
Minus 1.
Minus 1. And keep going on.
Minus 100.
Minus 100. Okay. So let's say that we have this. So the idea with the stack was that the numbers are coming in this sequence. Right? We maintain two stacks, the data stack, and we maintain another stack. Let's call it a MinStack. And what we are trying to do is create a stack whose basic operations are the usual, of course, pop, push, right, peek. But one more thing, min. It returns the minimum of the stack at that given state of the stack, given those elements in the stack. And the puzzle is, how do you do it in order 1? This thing, order 1 performance. Now, this is tricky because if this was not order 1, you could just have inspected the entire stack and found the minimum. Right? So that would be order n. So for example, if you have to find the min value in a given stack, and if that stack is all you have, what you can do is you can sort of keep popping up and figure out which is the min and then put all the elements back. Sort of that, or do it recursively or something like that. But the moment you say do it in order 1, then it gets more complicated. So what we do is we realize that we need to keep track of the minimum so that we just look it up and tell. Right? So if you have imagine that you have a variable min, right? And for the time being, just imagine that it's not the stack, it's just a variable. So what is min? When you have just 5 in the beginning, you put 5 here. In the absence of any other information, it as well is the minimum, right? But now suppose 4 comes in. Then 5 becomes the second smallest element you have seen so far, yes, isn't it? So you put 4 here, you put 4 here also. Then you come across 1, and well, 1 is smaller than 4. So you push 1 also here. But then now what do you have? You have the set of smallest, second smallest, and third smallest element that you have seen so far, isn't it? But then you come across 3. Let's think what we do. 3, of course, we push here. The question is, do we push here? 3 is bigger than 1, isn't it? So we don't have to push here because if 3 is lost, 1 still remains the minimum. So idea is that you can just peek at the top and see what is the minimum. If the stack is this much, well, 1 still continues to be the minimum, right? So we don't need to push it at all. Then suppose 2 comes. Well, the same argument applies. And so 2 and all the way up to, you finally get 0. Well, the moment you get 0, you realize that 0 is smaller than 1. Yes. So we have to put 0 here now, right? Then you move forward, and then I suppose you get a 4. You don't do anything with 4, right? Once again, if we pop 4, the 0 still remains the minimum. So there's no point in pushing it up down this stack. Then you suddenly come to -1, and so you realize you better put it here, isn't it? And then you get -100, and you put -100 here. So at this particular moment, somebody asks, what is the smallest amount in the stack? You say -100. But then what happens if you, now let's start popping from this. Suppose you pop this. Well, you have to remember, is this the smallest? If these two match, when you pop it from here also. If they don't match, then you don't worry about it.
Right? But popping happens...
Pop has to happen from the top, remember?
Yeah, last from the
top. Okay. And then -1 comes, you take this one also out. Then 0 comes, oh boy, this also will go away, right? But there will be so many elements when you pop from here, but you won't be popping from here, right? You'll be, many cases where you will pop from data stack, but leave the min stack unaffected, right? And that's the whole idea. That, for example, when you're popping 4, zero still remains. You don't pop 0. But and so we go when you pop 8, for example, when you pop 7, right? So there's 7 and 8 sitting here. Let's say 7 was sitting here, 8 was sitting here. So when these guys get popped, you don't touch 2, right? At that particular, where's 2 gone? Yeah, 2 is
not,
also, yeah, well, 2 is not there. You don't pop. Even when you pop 2, it doesn't matter. 3, it doesn't matter.
Yes.
But finally you get to 1. Now it matters because it is here. And now, because these two match, you pop these. Now this next smallest is 4, which is correct. If you look at this stack, 4 is actually the smallest element here. So what happens is at any given moment, or to do order 1 lookup of the min, you just have to look into the, peek into the MinStack. Right? And so you can implement what is called a MinStack using 2 stacks.
Yes. So this works in all cases.
It works in all cases.
I realize it works in all cases
now
because
I got your point.
because you're maintaining the lowest at a particular time.
Exactly.
If you do not maintain that, if you just maintain the minimum, when you pop the other guy, then that
You'll
value
be in trouble.
you'll be in trouble. So
The trouble is if you maintain only one variable for minimum, once that is popped, you're in trouble because you don't know what is the next minimum, what is the second minimum. But now, by keeping a min stack, the history is kept essentially.